Last topic in this section is another physics application, and that's the notion of work. So generally, when you apply a force on an object, if it causes that object to move, a force that causes motion is going to be doing work. And the simplest case we have is if you apply a constant force, and you apply that force in the direction of displacement. So if I moved an object from here to here, the displacement is going straight to the left. If I applied my force straight to the left, and it was a constant force, I would calculate the work by simply multiplying the amount of force. So this would be the magnitude of the force vector, multiplied by the distance that I had moved that object. So work is force times distance. That's the simplest scenario that we have, and that's going to be the basic model that we use to modify for the more complicated scenarios. The fact that this is our formula is sort of shown in the units that we use. So common units for work, common units would be Newton meters. Newtons are a unit of force, and of course meters are a unit for distance. Foot pounds are another common unit that we have for work. That would be where we're measuring distance in feet and force in pounds, as we did in the last example, because remember, the weight of an object is actually just the force of gravity. So what we often think of as units of weight are actually units of force as well. All right, now we're going to take a look at the more complicated case. We're still going to have a constant force. So it's going to be constant in both its magnitude and direction, because it's going to be a vector, but it's going to be applied in a direction that's different from the displacement. So this is similar to what we just saw when we had an object lying on a ramp. The force of gravity acts straight down, but the object doesn't fall straight down breaking through the ramp. The object moves down the ramp. So it's moving in a downward direction, but it's not moving straight down, so it's not moving in the same direction as the force. So let's just suppose I've got this. I'm going to have an object that starts at Q, P, and goes to Q, so that I'm going to be able to say that PQ is my displacement vector. I'm going to be moving things from point P to point Q. And let's just suppose that my force is acting like so. Now, if that's the case, I'm basically going to be able to use projections here to calculate the work that we're doing. Because I can see that this force vector I could write as a sum of two vectors. If I project onto the displacement vector, I'm going to get this. This would be the projection of the force onto PQ, and then this would just be perpendicular to that displacement vector. Okay. And it's going to be this component of force that's contributing to the work. If the object isn't moving in this direction at all, this component of force is being canceled out for some reason. In our example of the object on the ramp, the normal force of the ramp was canceling out the component of gravity that was acting perpendicular to the ramp. Okay. So this component of force is going to be doing the work. Now, if this force is constant, this component of the force is constant. So now I've sort of reduced this to, okay, I'm applying this constant force in the direction of displacement. So the work is simply going to be the amount of that force. So that's going to be the magnitude of the projection of the force onto PQ times the distance, and the distance is just going to be the magnitude of the displacement vector, because I'm traveling in a straight line. Now, if I'm traveling in a curved path, distance and magnitude of displacement are different. But if I'm traveling in a straight line from P to Q, then the distance that's traveled is just the magnitude of that displacement vector. Okay, excellent. So now, if I take a look at this, I can actually figure out what this is so that I can save myself a little bit of work. There's going to be a very nice shortcut right here. I'm going to just draw in my angle theta here, which is the angle between the force and the displacement vector. Now, I've drawn this in as an acute angle. That's because basically if I had an obtuse angle so that my force was pointing, making an obtuse angle there, so it was pointing off in that direction, there's no way that force would be responsible for the object moving in this direction. In order for the force to be the reason the object is going to move from one point to another, there has to be a component of that force that's pointing in the direction of displacement. If I had an obtuse angle, the component of force would be pointing in the opposite direction. We will encounter that situation later on in the semester. There we're going to basically be talking about negative work, where there's some other reason other than the force that the object is moving here, and the force is sort of pushing you back. That's like the scenario of if you're riding your bike into the wind is essentially doing negative work, and it's making you work that much harder to counter that. We're not dealing with that scenario right here. We're dealing with the scenario where this force is what's causing the object to move. And if that's the case, this angle does have to be acute so that there is a component of that force that points in the same direction as the displacement. So I can go ahead and use this picture. I want this magnitude, okay? I'm just going to call this right now, I'm just going to call it x, just so I don't have to write that. And I can say, well, cosine of theta would just be x over the magnitude of f, because I've got this nifty right triangle. X is the adjacent side here, and the magnitude of f would be the hypotenuse. So I can solve for x. X is the magnitude of f times cosine of theta. Okay, so if I go ahead and plug that in, and I think I'm going to just rearrange it, I'm going to put the cosine theta first. I'll have cosine theta, magnitude of f, times magnitude of PQ. Now that looks kind of familiar. That's a product of three things. The magnitudes of these two vectors that form this angle theta, and then cosine of that angle. Well, magnitude times cosine of the angle between two vectors, that's just f dotted with PQ. Very cool, okay? So if the general model for work is that work is force times distance, that applies when the force is in the direction of displacement, and it's a constant force. If I have a constant force that's in a direction other than the displacement, the work is just the force dotted with the displacement vector. Now, I can get that by working out this projection. But notice, if you remember the result, it's actually a lot faster to just dot these two vectors. If you forget that that's the formula, you can always work it out and figure it out and do the projection. But it's kind of nice to just have that shortcut. So let's try an example. Let's find the work done by a force that of, well, let's say, of 10 newtons that makes a 30-degree angle with the positive x-axis. If it moves an object 5 meters to the right. Okay, so if here are my axes, my force is going to look something like this, where that's a 30-degree angle, and the magnitude of the force would be 10. So I can actually write that out. My force vector will then just be 10 times the unit vector that makes this angle of 30, which is cosine of 30 degrees, sine of 30 degrees. So that's going to be 10 copies of root 3 over 2, 1/2. So that's just 5 root 3, comma 5. So there's my force vector. Now, if we're going to move the object 5 meters to the right, that's just my displacement vector would be 5, 0. We're going 5 units straight to the right and 0 units up. Okay. So I can say my displacement, I'm just going to call it D for displacement, is equal to, to 5, 0. So now I've got my force vector, I've got my displacement vector, and in this scenario, work is just force dotted with displacement. So that would be 5 root 3, comma 5, dotted with 5, 0. That's going to just be 25 root 3. You'll notice that work is a scalar quantity. It's not a vector quantity. And the units here would just be the units for force, which were newtons, multiplied by the units for displacement, which were meters. So that would be Newton meters.